Hi, everyone. Hope everyone is doing well. And we are very pleased to have Paul Müller today from Linz. And he's talking about complex convexity estimates and their extensions. Paul?
Thank you very much. And thank you particularly, Bunyamin, for organizing this webinar for an extended amount of time. And I think it was one of the backbones of mathematical exchange in recent years. So I enjoyed it very much. I'm talking about complex convexity estimates, in particular the best constants there, and the extension to higher dimensions, and the link to log-Sobolev inequalities. And this is a joint work with Pater Ivanishvili from North Carolina, and Alexander Lindenberger and Michael Schmuckenschläger, who are here at Kepler University in Linz. And I should say, we discussed it before, this collaboration started just half a year before the lockdowns and the pandemic started. So, and I would like to start with some background that we will leave eventually, but I want to point out that behind these particular inequalities we are talking, there's an extended theory. And the concept is the uniform PL convexity or uniform convexity estimates. This involves LP parameters between 0 and 2, and it involves capital LP parameters between 2 and infinity. And we say that the Banach space is R uniform PL convex if there exists a constant such that the LP norm of a given element, then two given elements actually, then multiplied with uniformly distributed zeta from the unit circle and integrated with respect to the normalized H measure, if this mean is larger than the LR norm, if you want, so the norm of x to the power r plus the norm of a to the power r, but the constants involved in these inequalities are all related to the second variable. If that particular addition wouldn't be present, we wouldn't be talking about the significant estimate, it would just be Jensen's inequality. And associated to this particular estimate is the search for the right exponents, as well as the search for the best constants. And this comes by, this is formalized by looking for the moduli of complex convexity, where we normalize both elements in the Banach space, x to 1 and here's the x, and around that x there is circling a times zeta, and we are subtracting here that value -1 that comes from this normalization. And this particular modulus of convexity is supposed to give you the exponent r. Okay, so this is how it is set up. And I'm particularly referring to the work of Davis, Garling, Tonczak, Jägermann, where they linked complex convexity estimates and the modulus to power type growth. Okay? So we are observing that the modulus of complex convexity behaves like epsilon to the r, and under this hypothesis, co-type estimates hold for martingales, but not for every class of martingales, but for a particular class of martingales called analytic martingales. And those are martingales where the increments in first of all, those are martingales on torus to the n, and the increments are given by zeta to the n times a weight that depends on the previous n-1 variables. And for this particular estimates, this power type of the convexity modulus gives rise to martingale co-type estimates. In particular, these estimates for analytic martingale hold in situations where they do not hold for general martingales. And the typical example for this is capital L1. And so this modulus of convexity is related to co-type estimates for analytic martingales. And then we have the search for the best constants in the complex convexity estimates. This is in particular a major theme in this paper. And so the spaces capital L1 and the trace class were of particular interest in that work, because there, as I said, the corresponding martingale inequalities for general martingales, other than analytic ones, are simply not valid. Okay? And the basis of that work, the analytic basis, is a complexity estimate, which is sharp in terms of the constant, and it estimates the average where X and A are complex numbers, and it gives the this particular complex convexity estimate for the Banach space before I formulated it for a Banach space E, and in this context, the space E are the complex numbers. Right? And in the paper, this particular estimate is proved with the best constant, and it turned out that before that, Mon Ami had this estimate proven in one of her papers as well. It simply the very elementary nature of this inequality. There could be double and triple proofs of that, and independent proofs and separate proofs, actually different proofs by Mon Ami and Davis, Carlington, Chegigerman. So I want to talk first, before I go into my work, I want to talk about extensions of these estimates. And so let me try to get some information from here and make this continuous. So we are having this particular inequality, complex convexity estimate for C. And here we are having one complex analytic variable. It's the analytic variable A zeta. And the extensions I'm talking about come by replacing first A zeta by an analytic polynomial. Zeta is still in the unit, in the boundary of the unit disk. And so the natural extension is what happens if we replace this particular simple variable by a more complex one. And there we have the estimate by Hagerup and Pizier, where they said they get simply the very same estimate with the same base constant, 1/2, and the G replaces the A zeta, and the absolute value of A simply could be interpreted as the L1 norm of G, which it is. Okay? And then this is the first direct extension with the same constant. Okay? But there's a different way of extending it. Namely, we could interpret this here also artificially in such a way. Namely, that we write it as the integral of x squared plus a constant delta times here would be the number A, depending on A times theta, depending on theta. In the original, let's see if I still have the same. Yeah, in the original version, A times theta square is simply absolute value is simply A. And so in the original version, the theta dependence of G disappeared, and it doesn't therefore matter if it's inside the integral or outside. Yeah. And so therefore this is a separate extension. And it turns out in the meanwhile that the best constant in this inequality is still unknown. And there are the original proof by Bourgain, who worked with factorization. So factorization is a way to express an element in H1 by the product of two elements in H2, and in H2 there's a corresponding version of this element which can be therefore extrapolated in a short description of what's going on in the proof. And if you analyze the proof, delta square is larger than 1/9, and for any delta square larger than 1/9. So actually it should be smaller than 1/9. Yeah, so, no, it's larger. Okay. And if you, another way of doing this comes from interpreting the right and the left-hand side in terms of Brownian motion. Yeah. And in terms of Ito's formula, and if you do it with Ito's formula, you get 1/6 as the largest constant known for which this holds. So this is what I want to say, the largest constant for which it is known that it holds. Okay. And all of this is worked out in a new book on Hardy martingales, which will appear at Cambridge University in the new mathematical monograph series, and it will be sent to the editors for final printing in June. Okay, and I know this because I'm going to send it to the editors. Now, there's another extension of the original inequality in, let me see if I go back. Yeah. The original inequality by Davis, Garling, and Tomczak Jägermann, or if you want, by Bonamy. And that corresponds by replacing the L1 norm on the left-hand side by an LP norm, and the P is between 0 and 2. And in that range, we have the work of Weissler and Alexandrov, who obtained complex analytic methods for proving that in this range, the P norm is larger than this expression that appeared before. That didn't change by its nature. It is x squared plus p over 2, a squared to the power p over 2. And in that case, p over 2 is the largest constant, and that fits exactly in the framework that we've seen before. So they obtain the extension for the entire range of values of p, and Weissler actually says he refers to an argument somehow shown to him by Svante Jansson. And it is presented by Weissler in his work. Okay? And the proof by its construction carries over somehow this factorization idea, and it starts with the L1 estimates and then pushes it down to 0. And it's actually, if you it's called Rees factorization for HP spaces, it was somehow devised as a tool for extrapolating H1 estimates to HP estimates with P larger than zero, okay? And now in this context, when we emphasize that the complex analytic nature of their proofs, there is somehow an extension to higher dimensions, for which really these proofs simply don't work and never were intended to work. And this is the theorem I'm going to talk about today. Okay? And this is the joint work with Pater, with Alexander, and with Michael. And so we obtained an estimate where we are considering the normalized surface measure on Sn-1, and we are looking at the same expressions as before. So we are having here elements in Rn, here, if you wish, here. Those are in Rn, and this is actually in n-1. And the constant A here is, we make positive, and since by rotational symmetry, this is a valid, there is no somehow loss of generality by limiting the range of A in this form. Okay? So we have here for A, we have a scalar, and the element in zeta, the previous zeta is a C in Sn-1. And for that, we have the same estimate in LP version, and we get the complex convexity estimate with x squared. At that moment, a strange looking factor, but it will turn out, and this will be part of the discussion, a very natural factor, times a squared to the 1/2. And if you check n equals 2, which was the case we considered before, the constant is really the same as before, and somehow it reduces to the same estimate. The tools involved should then be real variable in nature, and we mentioned that this is indeed, again, the best possible and therefore the largest possible constant for which the inequality holds. Okay. So, and before I approach the proof, I would like to make a connection. It's an incomplete connection, but extremely somehow. So this connection should be explored, and it really presents itself if one rewrites here this term simply in L2 Sn-1 form. Okay. So, and therefore I would like to make a digression. Yeah. And the digression is to make a convincing link to log-Sobolev inequalities. Okay. Yep. Right. And so first we rewrite the right-hand side, as we said, artificially in an L2 form. And there is nothing special if we evaluate this particular integral. These x and c are then also c's of mean 0, so we can write it out. And then to maybe I go back again. Let's see. Yeah. So on the right-hand side, in the normalization we discussed before, the right-hand side constant contained the p. And the strategy is to separate the values of p to the left-hand side. And this is simply done by considering, instead of A, a rescaled version of A and call it B. Okay? And that kills this factor on top, and it brings it over here. It's a simple procedure. And now the variables are fully separated. And since the variables are separated, we may look, and we find that, of course, the family of expressions on the left-hand side are, in the particular case of p equals 2, correspond to the one on the right-hand side. And this inequality we know, okay? So we will prove, and that's a theorem. Yeah, that's a theorem. Now the conjecture is that instead of having the value 2 on the right-hand side, we have any q larger than p on the right-hand side. And the form of the right-hand side really also presents itself because it is already present on the left-hand side of the known theorem. And this conjecture, as it stands here, is the conjecture, well, we couldn't prove, but it is, I would like to show how much of it we could prove. And so this is the next page. So if we play this game, or if we are trying to establish these inequalities, and if we restrict the range of P to the region where P is larger than 6, and 6 is a random number, okay? Then independent of what n is, we have this estimate. Yeah? And about this, I would like to talk, and here I would like to express also, also to describe also the approach we are using. Yeah? And so, and the ingredients we are using, and so starting from, this is the theorem that will come. The conjecture is that this restriction here is, of course, unnecessary, and the real range is from 0 to infinity. And so we discuss how we do that. So, so the variables we are interested in are built by fixing an element here and another scalar parameter b, and forming a function that depends on p. And we form exactly the expressions that we had on the left-hand side of our inequality. And then, of course, if we can show that phi prime is negative for the entire range, ideally, but if where we can show that phi prime is negative, there we know that the inequality we are after is true. And therefore, we want to calculate phi prime. So we do some elementary calculations and some arithmetic, and we look at conditions for phi prime is negative. Okay? And therefore we rewrite the formula for convenience with an exponential, because then we know that, and then we differentiate with respect to p, and at least we should mark all the places where p appears, and these are 3. And at all those 3 places, with respect to this, we have to find, so we have to calculate. And this leads then to the following expression first, that phi prime over phi is a huge expression, okay? And what I would like to point out is that here again, here already, the logarithm of the original function appears, and it appears naturally out of the calculation. And then there are separate terms, and one of it is still not x'd out, that is the term where the differentiation with respect to the internal P appears. That will be done later. But I would like to point out that this function phi itself is larger than 0, and this term here is also larger than 0. So if we multiply with the term here in the denominator, we don't change the conditions we are looking for. And if we calculate this, then terms will simplify or not simplify, but they will be explicit then, and we have something to look at. And that is what happens here. And this is the summary of calculations. Okay, this is calculus. Whatever. Okay. We simply have a term of the form x plus a to the power p times the ln, and I left it there. I could move the p out. Minus x minus ac to the power p times the ln of this expression. And this is not random here. And I will show later why it's not random. And all other terms are simply the result of a calculation. This comes out. And this is the moment where we step back. And so we know that this condition we are interested in, phi prime is negative, is equivalent to an integral inequality with a lot of complicated terms, but the left-hand side has a particular structure. And this structure we would like to exploit a little bit. And now we are comparing this to a known inequality. It's the log-Sobolev inequality for the sphere. And that it is for the sphere, I would like to go back. All integrals here are over the sphere, etc. Okay? So it is for the sphere. And this was obtained by Beckner in his sharp Sobolev inequalities on the sphere and the Todinger inequality. Okay? And it reads as follows. It's an inequality for every f and non-negative. So it's rephrased in such a way that that we can directly compare it. It says, given any f squared times the logarithm of f squared minus the 2 norm, so f squared d sigma, times the ln of the 2 norm is bounded by. And this bounded by, here is a constant, 2 over n minus 1. And then there is a gradient. And the gradient is the spherical gradient. And the spherical gradient is relatively direct to compute. You take the standard gradient at a point x, look at the tangent plane to Sn minus 1 at a point x, in our case it's c, and then project onto it. Yeah? So the tangent plane at c and is the orthogonal complement of c. Okay? And these are the two procedures one has to do if one wants to compute the gradient, the standard gradient, and then project it. And we are going to test this inequality for the functions we are interested in. F of c is x plus a times c. A is fixed, p is fixed, x is fixed, and c is the variable. And for it, so if we take this f, plug it in on the left-hand side of the Beckner inequality, we find exactly what we calculated before. This is the arithmetic was set up so that these two lines match. And then Beckner tells us this expression that we were somehow observing is bounded by this integral of the spherical gradient. Right? And now if we calculate it, our problem reduces now using Beckner. Okay, I hope. Yeah. So in summary, the condition phi prime is negative is implied by the inequality that we know holds true. So the left-hand side by Beckner is bounded by the L2 norm of the spherical gradient, but we would like to have this expression as an upper bound for the left-hand side. And the only way we can imagine is, let's try to estimate the L2 norm of the spherical gradient by the expression that we inherited by our calculations. That's the plan. And so, and this, the spherical gradient is here calculated. And then it turns out that this is an inequality, and typically you think it's a matter of 10 minutes because all terms are explicit, and here we are looking at the gradient squared. We can of course calculate this also, and then it's true or not true, and you hope it's true, and the value for which we can find it is p larger than 6. And since there are several other related log-Sobolev inequalities, this is not the one which appeared in our paper, but it was transposed into another form due to Carl Müller and Weissler, slightly, I think, before Beckner's inequality, but in the same range of years. So, so this was the link to the log-Sobolev inequality, and it is extremely tempting to follow this approach, and it turned out to be not pleasant to verify, unless this is the range. The conjecture is it holds, this inequality holds for every p larger than 0. So now we are supposed to return to our theme, namely the theorem. I would like to sketch the proof, and that is the inequality. We are in over Sn minus 1. We are seeing the terms x plus ac in the p norm with respect to normalized surface measure, and we are here having this complex convexity estimate with the constant that we are talking about, that we know is best possible, that we knew actually before. And actually in that form, the form of this inequality and the fact that these constants can be factored out, the p can be factored out and brought over here, this was the beginning of why the log-Sobolev approach is just possible. Okay? And here, other than in the other approach, we notice that we have 3 cases to consider, and the cases depend on n. The case n equal 2 and n equal 3 are practically the same in our proof, not as letter by letter, and totally separate is the case n larger than 4. And this is now what I want to discuss, and we'll see in which detail that will be. Okay. So first we look at the case n equals 2, and I just list the ingredients that play a role, and I say fully play a role. And one is Jensen's inequality for the analytic function x plus zeta a. For that analytic function, Jensen's inequality gives us an equality to that term. The integral of the ln of absolute value x plus zeta a is equal to ln maximum of x maximum of a. Separately, and yeah, separately we use the arithmetic geometric mean in all in both ranges. with positive exponent and negative exponent, and we are comparing it to the expression that comes from Jensen's formula. And then we are using a standard trick in all this Hardy space field, namely to express the line integral over the boundary by the area integral over the disk. So this is d theta, dr is in reality the area integral over the disk, and for that we use Green's identity. Okay. And finally, there is a version of Bernoulli's inequality, which in the standard form reads like 1 plus rx is larger than 1 plus x to the power r in this range of r. And if we take for r equals to beta and for x equals to beta t, then we get this form of Bernoulli. Yeah. And these are the four components of the proof. And as we go over the dimensions, some of these components will remain the same. In particular, always this one, and also this one. Funny, as well as the arithmetic geometric mean. But around here, we are seeing rule changes. Okay? And now I would like to sketch the proof of this inequality, and in a sense, maybe I should say, I just say it as it is. This is not the best proof in dimension 2. The best proof probably is the one by Alexandrov, in the sense the most efficient presentation of this argument of this inequality is in Alexandrov's paper, but it is a version of the dimension 2 proof which extends to higher dimensions. Okay? And in particular, we will see. So first of all, maybe I should go back one line, one page, and an effect of Green's inequality. So what do we see here? Technically, we see here a positive exponent here, and we see here a negative exponent because our p is less than 2. Yeah? And this is the reason actually why, by way of Green's inequality, both parts of the arithmetic geometric mean come in. Yeah? And therefore, the original, so the proof now, so the proof begins by an analysis of the exponent p minus 2, because that is the exponent we inherit from Green's inequality. And so here we are in the negative range. So it is, p minus 2 is negative, and therefore, and this is also negative, and therefore we have an extension using exponential integral ln, and inside we are seeing an integral to which Jensen's inequality, or Jensen's formula, by the way, applies. Okay? And this is what we get from it. And all we needed, so while Jensen's formula gives equality, all we needed was this. And then we have Green's identity. This is the term we start with. This is what Green's equality identity gives us. And here we see already the terms we are interested. Yeah. And then we have an expression that just comes out, and it's a radial expression. It depends on R only. And this radial integral can be computed, yeah, and elementary. Yes. So, and we evaluate it. Here is the value, simple as, so it's not simple as that, but this is the outcome. Yeah? So there are two ranges for a larger than 1 and for a smaller than 1. And that, of course, the origin is already determined by the splitting of the integral here. And now it is a matter of getting a numerical expression for what we inherit. So we inherit that by Green's, we inherited this. And the psi is given by an explicit formula. And then in some elementary arithmetic, we find, with Bernoulli, we find the link to the term we want to find, namely 1 plus p over 2 a squared p over 2. And then finally, we note that by Green's identity, we have this link. Okay? So, and this is a sketch of a proof, which is definitely not the most elegant one, but it has the potential to extend to higher dimensions. Yeah, and this is what I'm going to sketch now. And actually, there is a different range for A, and I would like to skip this, simply because that is not where the difficulties arose in that proof. Yeah, and now we are looking at the ingredients for n larger than 3. Okay. And so what the first one before was Jensen's formula, and this time it is the question, when is the absolute value to the power q subharmonic? Or just we begin by the formula for the Laplacian of absolute value to the power q of an x in Rn, and for simplicity, so for safety reasons, this is not 0. And we find a formula, yeah, q and q plus n minus 2 times, it's a term, but this term is always positive, but this term is not always positive. Now, that has a consequence, namely, that determines when the absolute value to the power q is subharmonic and when not, and the relation between the dimensions and the value of q makes this difference. Then we have a Green's formula in higher dimensions, exactly divergence theorem, Gauss-Green-Stokes. We have the term that we are interested in here, and we have something to inherit. What is important for us is, again, a spherical integral and with the parameter p minus 2 as before, and all other terms are a result of applying Green's theorem. And then there is an additional component in the proof. This is a negative exponent, and for any negative exponent and any positive number r, we have a formula called Bochner's formula. And this is the third ingredient that we are going to use. And then I would try to see how those ingredients, all those three are relevant in the entire range n larger than 3, but then 3 and larger than 4 need a distinction. And so we discuss first n is equal to 3, and we restrict here to p less than 1. In that range, between 1 and 2 is of a different nature and simpler. Okay? Everything that is below 1 is the case of interest. And so in n, if n is equal to 3, we see that the Laplacian of absolute value of x to the p minus 2 is this term. We determined that before. And now we look at the p minus 1, p plus 3, that's n. And then because p minus 2 and then another minus 4. So this is minus 1. And this is larger than 0 in this case. And so here is the value 3 that, that somehow makes this factor positive, and then therefore this function is superharmonic. And therefore this integral larger than this maximum. And in that sense, having this estimate for the integral to the power p minus 2, for that purpose, we use the Jensen's formula in dimension 2. And now we have it due to the superharmonicity of the Laplacian. And once we have this, the same calculus gives essentially the inequality we are looking for in this case. And in the case n larger than 4, we calculate again the Laplacian, and we are simply now forced with a negative factor and a positive factor. And therefore the product is not positive, and therefore this function is not superharmonic, and therefore we have no replacement for Jensen's formula. We need something else. And I will not go to the end. I will just want to give the first page of n larger than 4, or maybe also the second page. And I would like to point out what we are doing now when this expression is not superharmonic, and which was really essential in all the other dimensions before. And for that, we use, for this particular term, we use the Bochner formula with the involved zeta, with it was minus zeta and therefore p minus 2. For that, we plug in, after that Fubini, we plug in exactly what we get. Okay? And then this particular expression splits into two. There's one expression, like here, which depends on the scalar product of x and c, and there is one expression which depends on all absolute terms, so which are independent of the scalar product. Okay? And there where the scalar product appears, this is where the integration appears and has an effect. Okay? So this part where the integration arises, it transforms into the cosh of the absolute value, simply because for each positive element we have a negative element, and these things cancel out. Yeah. So we have this formula, and now is the point. So we said rotational invariance. This is the case also where internal oscillations are taken care of. Right? Now is therefore the time to estimate. So the integral that we are interested in is this one. And we have taken care of the internal oscillations, and we are somehow left with the factor we had before, and the factor with the cosh under the integral. And for the cosh, we now try and test pointwise upper estimates. Yeah, the one that definitely holds is 1. The one and doesn't somehow, it's not conclusive. The second approximation is is therefore s squared. And then finally also we use an identity on the 2 norm of the absolute value of the scalar product as 1 over n. This we need for later, but now we put this particular cosh and replace it by this term. We abbreviate, so this is the place where this is done. Okay, so therefore we showed all these calculations based on Bochner's formula. We showed that this particular function is dominated by the function we are interested in, namely this integral of the spherical integral to the power p minus 2. Okay? And now in this formula, we can use Bochner in reverse direction. And therefore we find a formula for psi. Formula in A. And the factor which simplifies considerably due to identities for the gamma function. Okay? And then there is now the summary, and there is the summary of what we've done before. So we identify the function psi. U is now, U is A. Oh, U is A, because the A remains here. And that function we related to the integral that arose after the application of the divergence formula. And so we formed an expression f star with the constants that arose from Green's formula and with the estimates of the internal spherical integral, which was estimated using Bochner's identity. And then therefore, the original expression to which we applied Green's formula is larger than the expression we found here. And this, out of this integral here, all spherical components are estimated out, and we are having a radial integral in front of us. And by additional arithmetic, we are able to get the pointwise estimate for this f star, which is the lower bound for the integral we are interested in, by the term on the right-hand side that we want. And that is here. And in this calculation, the estimate, the restraint n is larger than 4 makes that work. And I think with this sketch of both proofs, I would like to stop. And I thank you for the attention. Thank you very much.
Thank you, Paul. Are there any questions or comments?
Yes, Paul, thank you for this nice lecture, and hello to everyone. If you replace in your main theorem, this may be implicit in what you did, I don't know. If you replace AZ by some function, G of Z, do you obtain a similar inequality? Instead of taking a linear function, if you take some function of the variable Z, can you get the similar result?
A good question. If you're looking, if you're somehow focusing on the Rn version, so then there is an, yeah. So we have no luck in extending this to higher, as it's done in the complex case, to higher terms.
Okay.
Other than the linear case, if you want.
Okay.
The two versions that would present themselves are already somehow models for it in dimension 2. This is the estimate by Hagerup and PCA, if you want, and yes. on one hand side, and the other estimate would be the one that where the square root, the absolute values are inside the integral. That would be the Pogain version. But I want to say, the point is the same as with Alexandrov's proofs and the other one. So the starting point to extrapolate is that is what it's called inner-outer factorization or Riesz factorization. So one element in HP, P is 1 over 2 to the n, is written as 2 to the n factors of elements in H1. Okay, and then so replacing these complex analytic methods, honestly, is here the stumbling, one of the stumbling blocks as such.
Thank you.
Yeah. And it looks like we need a post-pandemic meeting of all 4 authors to focus on this in with more strength. But yes, thanks for the question.
Any others? Okay, then thank you so much again, Paul, for a nice talk. So maybe we can stop sharing and then continue our conversation.